Okay, good morning, students. So we are into the week. What week is this? What week of your semester? Week 9. Okay, so week 9, 9, 10, 11, 12. Okay, 4 weeks more to go. We are 1.5 chapters away. Okay, so to complete the syllabus. So halfway through the almost. Okay, so hey, what happened? Oh, no wonder. I have not fixed the. Sorry. So from the last session, okay, so we have gone into to discuss about the stability of the nucleus. Okay, so which is we have learned about the mass defect and the binding energy. Okay, come on, students. When you come in, close the door behind. Thank you. Oh, you before start class already sleepy, yes. Okay. So mass defect and the binding energy. So I did give you a small brief on that. So when you refer to mass defect binding energy, so the mass defect is the loss in the mass during the process of nuclear decay. Okay, so fusion or fusion reaction, whereby whatever the loss in the mass is what has been converted to a form of energy. Correct? Correct or not? Okay, so during any nuclear decay, there will be some loss in the mass when you compare between the mass of the individual protons and neutrons when you add up. Okay, when you compare with the total mass of the nucleons, okay, so which is basically forms the nucleus. So that energy that has been released during this process is known as the binding energy. And binding energy, it is taken, I mean, the binding energy, okay, what is the conclusion or what we can further analyze by referring to the value of a binding energy. So binding energy, it is something that we can use to measure the stability of a nucleus. Okay, so the higher is the binding energy, meaning the more energy that is given out, that means the nucleus that has been formed, it is a more stable nucleus. So later you will look into, there is a table, okay, a graph, which shows how the binding energy changes for nucleus. Okay, so when we compare between the number of nucleons, okay, so a number of protons. So how the stability of the nucleus changes with the number of protons or the binding energy. Okay, so that one we will go into later. So had your breakfast already? Okay. So the difference between the sum of the mass of the individual protons and neutrons in the nucleus and the mass of the nucleus, it is the measure, okay, so of the mass defect, the difference in the mass. So we have seen that if you want to find the mass defect, the formula, okay, so when you say a mass defect, we are basically looking at the nucleus, okay. So therefore, you must take the total mass of the proton plus the total mass of the neutrons, you minus the nuclear mass, which is the total mass of that nucleus. So that will give you the mass defect. So if you are referring, it can be also based on the mass of the proton. Okay, so this is that was the first one. Or we can also base on the mass of the proton. Z is any number, I mean, that's actually referring to the number of protons, Z. Okay, so if you have the symbol for the nucleons, we have usually AZ1. So the A is referring to the number of nucleons and Z is referring to the number of protons. So therefore, if you want to find the total mass for the protons, then you must take the number of proton, you multiply by mass of one proton, which is equivalent to 1.67 times 10 power of minus 27. Then you plus with the number of neutron. So number of neutron will be your nuclear number A, okay, so minus the proton number Z. So that is A minus Z. Then you multiply by mass of a neutron, which is also 1.66 times 10 power minus 27. Okay, then you minus the atomic mass. Okay, so the minus the atomic mass minus the mass of the, okay, so the what is that, the electrons. Okay, the Z is, because when you say a nucleus is a state, it's a neutral nucleus, meaning the number of proton and the number of electrons has to be the same. That's why in the formula here, it is Z multiplied by the mass of one electron. Okay, so this is a way you can calculate out the. So here, if you say, in this case, this is the mass of the nucleus. So I mean nuclear mass. So the nuclear mass, okay, it is also equivalent to the atomic mass minus the mass of. So it's the same. This thing is the same. Okay. So the atomic mass minus the mass of the electrons is also equivalent to the nuclear mass. Okay. So which is everything. Okay, so when you're referring to the proton plus the neutron inside. On the other side here, we are finding the mass of the proton and neutron separately. Okay, so I hope it's simple, but then sometimes it can get confused. Okay, so make sure that you are clear with the difference between finding the mass of individual proton neutrons, okay, and also finding the mass of the nucleus as a whole. Okay, so when you say mass of the nucleus, okay, so the nuclear mass, it comes a combined of proton and neutrons into. Okay, so therefore, when they are as a whole, definitely there will be some loss of mass, because from the individual protons and neutrons, they come together to combine to form the nucleus. So during that, there will be some energy given out, which is in the form of a loss of mass. Okay. So here, this gives you even a much clearer uh, picture of the idea. So if you look at the nucleus, I mean the atom here basically. So this is the whole atom. Okay. So this is the whole atom. Okay. Make it okay. The whole atom. So in the atom, you have the proton, you have the neutron, you have the electron. So therefore, separate into the components. So you are separating it. Okay. So then you have your the protons. So neutron. Okay. Proton, neutron. Electrons are because electron it is always related to the because when you have one proton, one electron. So it is balanced. The nucleus will be a neutral nucleus when it has same number of proton and also neutron. So this is it has two protons and two neutrons. Therefore, this is known as the deuterium, one of the isotopes of the hydrogen. I think when you do chemistry, then you will know about this better. Okay. So then now when you look at the mass of the here you have two sorry, oh, 4 2. So this is actually 4 2 because I have 1 2 3 4 4 nucleons number and 2 protons. So this is actually a helium. Okay. So but then it is a combination of two hydrogen atoms. Okay. Because hydrogen, okay, so you have one proton and one neutron. Okay, so one it is an hydrogen monotherium. Okay, so let's see here. So when we take it as a helium as a whole atom, so the total mass of the helium atom was calculated 4.02260 U. Okay, so that is the helium atom. Then when we look into the mass of the nucleons separately, so therefore I have two hydrogen atom. Okay, so it is equivalent to 2.01566 U. I hope you remember what is the U value, correct? Okay, so the U is the unified atomic mass value, 1.66 times 10 power minus 27. So then I also have two neutrons. Therefore, it is mass given. Okay, so when you add up this, when you take the mass of the hydrogen atom, okay, so plus the mass for the two neutron, so you get the total mass which is equivalent to 4.03298 U. When you compare this value with this, you can notice that, okay, so when it actually forms the helium atom, there is some loss in the mass that taken place. So when you take the mass of the atom, hydrogen atom, plus the neutron, when you minus off this value, which is the mass of the helium atom, so you can see there is a difference in the mass. So that difference in the mass is the mass defect. And that is the mass which has, why there is a mass defect? Why there is some loss in the mass? Because that mass has been changed into a form of an energy. Okay, that is the binding energy that is being released. Okay, any questions on that? Okay, I think did we discuss the question number 2? Yeah. Okay. I have uploaded, I mean, back this. So, so as we whatever discuss questions we discuss when you write out. Okay. So I will try to uh, share it back. Okay. So into the okay. So, so question 2 done. So moving on. Okay, so this is the conclusion of what we have discussed. So mass energy equivalent. So energy is being converted to a form of mass. Okay, so where mass is a form of energy. So this is what stated by the Einstein's equation E equals to mc squared, where the m here it is the mass defect. Okay, so which measures, I mean, we can use this formula to further calculate the amount of energy that has been released during the process. Okay, so E equals to mc squared. Whatever the energy that is emitted, here we are looking at an energy as an electromagnetic ray. So therefore, it will have a speed equivalent to speed of a light. Okay, so then this is a form of an energy that is emitted. It is like a photons. Later, when you go to the last chapter, we will discuss about the term which is related to the photon. Photon is referring to a group, a discrete packet of energy. So usually when you talk about lights, electromagnetic rays, so these are the energy in a form of photon because they come in a group. Okay, they don't come as individual particle. If I take an object and I throw to you, that is just an object. Okay, so once it reaches to the place, done. The energy already transferred. But if you are looking at a light here, since these lights are continuously, energy has been transmitted. So it is not like one particle. It is a group of photon energy. So that's why light, okay, so it is grouped as a photon. Okay, it is a packet of a energy of electromagnetic ray. That is the explanation. Okay, we will see that in the last chapter. Okay, so photon. Okay, you can Google and find. So PHOTON, photon. So we refer to electromagnetic ray, okay, energy, because they come as a packet of energy. Okay, not individual. Okay, so this is done. So have you wrote on top here? Just write your classroom. Oh, who submitted? Remember, okay, so I want you to write your class group on the right hand corner on top. So this one, Tan Cheng Kiat. Where? So just now you submitted Tan Cheng Kiat, actually Tan Yong Ji and Tan Liang Ji. Okay, so can you please write on top? So easy for me to, because one group, okay, so they got 8 groups. Okay, so that will take some time for me to, because I need to divide it first. Okay, so before going to the next stage of process. Okay, mass energy equivalent. Values are obtained using constant with only 3 significant figures. Okay, so this is to fill up. Okay, so we want to fill up what is the energy. Okay, when you work out for 1 gram. Okay, so in unit of joules and MeV. Okay, so in the unit of joules and MeV. Okay, so first we'll work it out for joules first. Okay, then we'll go to MeV. See, energies, generally, when you refer to energy in your mechanics physics, energy is given in the unit of joule. Okay, so, but when it comes into discussion about energy in a much micro level, when you say a micro level means it's a small energy between the particles. Okay, so energy in quantum physics when talk about the particle movement and so on. So the magnitude of the energy is very small. If you were to give it in joules, the value will be like power of minus 19 and so on. So it's a very small value. Therefore, they have adopted a unit to represent for the micro energies. So this unit of energy, okay, so is either is EV, electron volt, okay, so you have electron volt or mega electron volt. So these are the other adopted units for energy. Other than joules. Joules is the common. So usually we use for large values. But when it comes to small values, then we will use EV or MEV. Okay. So I would like you to calculate, fill up the space there. Okay. So for the mass of 1 kg, for mass of 1 U, okay, and then the energy mass, so we want to find, so energy 1 joule, okay, so this one is just conversion mean 1 joule mean basically this is in term of joule is just 1 joule, but when you convert to MEV, then okay, so how we do that? Okay, we'll come to that. So how do we work out first energy? Okay, so for one gram. So if just say if there is a mass defect of 1 gram, so what will be the amount of energy? So therefore, when I use the formula E equals to mc squared, sorry, delta M. So we will use that. In fact, I will write the formula on top lah, easier. So we are going to use the formula E equals to delta mc squared. Okay, so now when you can calculate for the amount of energy for 1 gram. So it will be delta M, it is 1 kg. So also the 1 gram, we must change to kg. So then it has to be 1 times 10 power of minus 3. So now it is in kg. You multiply by 3 times 10 power of 8 squared. So that will give you the answer. Okay, work it out. Complete that first. So 1 times 10 power minus 3, you multiply by 3 times 10 power 8 power square. So what do you get? 9 times 10 power of 16. Then you multiply by 1 times 10 power minus 3. So basically, you're going to have 9 times 10 power of 16, take away 3. So you have 13, correct? So that is your joule. That is in the unit of joule. This is quite a large energy because the mass is 1 gram mass defect. Okay, so 1 gram, probably you think 1 gram is not a huge mass. But in terms of when we refer to related to the nuclear processes, that 1 gram is a large amount of mass. That's why in the nuclear energy, okay, nuclear bomb and so on, you can see the amount of energy that is produced is huge because, okay, so that is experiences a larger uh, change in the mass, which leads to a greater amount of energy that has been produced. So then from there, how do I change this to MEV? Okay, from joule, how do we change to MEV? So when you are changing from, okay, so joule to MeV, okay. So M is actually stands for mega, 10 power of 6. And E is actually the charge of electron, which is 1.6 times 10 power of minus 19. Okay, so coulomb. So minus 19 coulomb. So when I say energy equivalent to 1 joule, so if I were to change this to MeV, so that means, okay, so I have a mega electron. Okay, so this mega is the effects. Charge coulomb. This is volt. If you look back to the formula, potential difference is equal to work done per unit charge. Therefore, work is equal to potential difference multiplied by the charge. Meaning work, the unit is joule. So the unit for volt, okay, so V, and here is coulomb. You can see that joule is also equivalent to coulomb volt. So the unit of joule, okay, so it is the simplified SI unit. Okay, so it can be also equivalent to coulomb volt. Okay, but that we simplify to put in joule. So in this case, yes, it justifies. I have coulomb, I have volt. Okay, only thing is I'm trying to add this. So therefore, okay, so when I put in mega electron volt, so 1 MeV, okay. So this has to be divided by times 10 power of 6, that's the mega, times 1.6 times 10 power minus 19. Okay. So I balance. So I have a mega electron volt on top. So and then I have substituted the values below. So now I need to solve this. So when I solve, okay, so 1 over, this is 1.6 times 10 power of minus 13. Okay, so I have 1 MeV divided by 1.6 times 10 power of negative 13. So then when I bring it up, 1 over 1.6, what do you get? 1 over 1.6. Power of minus 13, I bring it up, will become times 10 power of 13. 1 divided by 1.6. Yeah. 0.62. So 0.62. So this will be the MeV. But then you must change to standard form. So 6.2 times 10 power of 13. Not 13, sorry. 12. I move. Okay, 12 MeV. So this is how you do the conversion. But usually for large energy, we don't do that because this looks more complicated. Okay, so a large value, this looks more complicated. Okay, 6.2 times 10 power of 12 MeV. But if just say those, if in case if you go back, not able to see, okay, so later you can take the picture. See if it is, there's no light here. Okay, 1.6 times 10 power of minus 19 joule. Okay, so if I were to change this to MeV, then 1.6 times 10 power of minus 19 MeV divide by 1.6 times 10 power of minus 19. Okay, so then you have your times 10 power of 6 mega. Okay, so therefore, in this case, this can be cancelled. So we bring it up. Okay, so then 1 over, so it's basically 1 times 10 power of 6 mega electron volt. So from 1919 joule, we convert to 1 times 10 power of 6 mega electron volt. So this is conversion. So whenever you want to change from joule to MeV, you need to divide by the charge of electron and then what's that? And the mega. So here you do the same thing. So when you want to change, so I have 9.13 times 10 power of 13. So mega electron volt. So I must divide by 10 power of 6 times 1.6 times 10 power of minus 19. Okay, now you simplify this. So whenever there is a charge of electron multiplied by mega, automatically it will become 1.6 times 10 power minus 13 because you take 6 away from minus 19. Okay, so then when you solve this, what do you get? 9.13. Where go 9? Oh, sorry. It's 9. It is 9. Okay, so not 9.13. It's just 9 times 10 power of 13. Okay, so therefore, when we solve this, you have 9 times 10 power of 13 divided by 1.6 times 10 power of 13. Okay, power of 13 above and power of 13 below will cancel. So in this case, 9 divided by 1.6, what do you get? See, 5.62 MeV. So it is being simplified. So 5.62 MeV is equivalent to 9 times 10 power of 13 joule. Okay. So if they say from 5.62, see from 5.62 MeV, if I want to change to joule, I will take 5.62 times mega times charge of electron. So this will convert back to joule. Work out MC. Did you get back the answer 9 times 10 power of 13? Work backward. So 5.62 times 1.6, what do you get? 5.62 you times 1.6, what do you get? 8.99. So then 8.99 times 10 power of minus 13, correct? So you go back to 9 times 10 power of 13. So this is how you convert from the MeV to joule, joule to MeV. So MeV to joule you multiply, joule to MeV you need to divide. Okay, so here you can see we have done the dividing, okay, to change from joule to MeV. Okay, so any question? In between, I did mention electron volt. So if you want to change, changing to electron volt, okay, so instead of divide by mega, if you just say if you want to change to electron volt, then you don't need to divide by mega. It's just the charge of electron. So then you will change it to just EV. So there is no mega involved. So if MEV, mega electron volt, then you have the mega times the charge of electron you divide. And here, okay, so If it is just say if you have 1.6 times, if it is 1.6 EV, example, then 1.6 EV, if you change to joule, it will be 1.6. Okay, so then you times by 1.6 times 10 power of minus 19. Okay, so joule. Then it work out. Okay, so in this case, you don't multiply by mega. You just multiply by the charge of electron. Okay. So just now when you work out, this is okay. So you have 5.62. Okay, now try to work for 1U. So if it is 1U, your mass defect is 1.66 because 1U is equivalent to 1.66 times 10 power of minus 27. That is the equivalent for 1U. Okay, so here, if you see bottom here, 1.66 times 10 power minus 27 kg. That multiplied by the speed, okay, so which is 3 times 10 power of 8 square. Okay, now you get your energy in joules. And whatever the energy answer that you get, if you divide by the mega electron, then you get in MeV. Okay, can you give me the answer for 1U? 1.66 times 10 power minus 27 multiplied by the speed of light square. What do you get? 1.44. 1.494. 1.494 times 10 power of, yeah, 10. Okay. 10, this is joule. Okay, can you calculate for the MeV? It should be somewhere about 900 something, 930 something, if you change to MeV. You must take 1.494 times 10 power of 10. You divide by mega electron volt. What do you get? Oh, yeah, it's supposed to be negative 10. Yes, not positive. Because you have minus 27. And over here, you have only power of 16. Okay, so minus 10. Okay, there's a minus 10. So what do you get? So 1.494 times 10 power of minus 10, you divide by 10 power of 6 mega times 1.6 times 10 power of minus 19. So 900 what? 63. Yeah. Okay, 933 point something MeV. Okay, this is actually a standard calculation. So whenever there is a mass defect of 1U, a mass defect of 1U, it is equivalent to 933 or 34. Okay, so depending when you round up, exact value what? 933.75. Okay, so that's why it will come to 934. So it is a standard equivalent. Always you will say any mass defect of equivalent to 1U, it will give you an energy of 934 MeV. So this is calculated by using the formula E equals to mc squared. So if 1U is able to give you 934, if the mass defect is 2U, how much? Times by 2. So if 1U mass defect is able to give you 934, so 2U, okay, multiply by 2, 934. Okay, 3U, 4U, okay, so it just multiply. Okay, so according to the number of U. Okay. So then so this one, okay, just converting. So meaning if it is 1, as mentioned just now, so 1 joule, if I were to change it to MeV, so then I have to divide by 10 power of 6 times 1.6 times 10 power of minus 19. So then you have converted that into MeV. Okay, so I think now you will understand. So in order to change to MeV, the energy in joules, you need to divide by mega and a charge of an electron. Okay. And if you want to change to EV, okay, you see the EV later when you come to the last chapter, okay, when you discuss about, especially when you go into quantum physics region. Because the reason why we use MEV, EV here is the amount of energy that is involved in the discussion is very small. So therefore, if you are going to use joule, okay, so if, for example, if you see for 1U, the energy in joule is 1.494 times 10 power minus 10. But, okay, so when you refer in term of MEV, is 934 MEV. So easier to remember these values. Okay. So this is what we have basically worked this now. Okay. So here it has been worked out. Okay. So to show you the 1U equivalent to, so 931.5 MeV over the C squared. Okay. So it don't. So MEV. Okay. So the C squared, we already calculated that into the formula earlier. So that is the value. Okay, so therefore, okay, so it's just 1U equals to 931.5. Okay, so but we work out is 934. Okay, sometimes it's due to the decimal calculations that is involved. Okay, so no need not to worry about that. When you are doing calculation, whatever the values will be given to you, and then you use accordingly. Okay, so on the significant figures that is given. So this is value in actual value that you obtain directly from your calculator. So the values that you see here. But not necessarily you must use the whole thing. Okay, you can just base on the what is provided in the question. Okay, so moving on further to discuss on the binding energy. So the energy required to separate the protons and neutrons of the nucleus into the separate individual nucleons. So when you want to define the binding energy, okay, we know binding energy is a measure of the stability of a nucleus. But how do we define the binding energy? So to define the binding energy, so you will say it is the energy that is required to bring all the nucleons, separate nucleons, to form the nucleus. Okay, so as mentioned, so it's required to is either it can be defined as two ways. Is either you want to bring all the nucleons together to form the nucleus, or to break to break the nucleons to separate nucleons, from the nucleus to a separate nucleons. So that's what the energy required to separate the protons and neutrons of the nucleus into a separate individual nucleons. So you can see in this process, so the energy is required to break this so that they become a individual nucleons. So the amount of energy that we need to break them, okay, so it is the binding energy. And if more energy is needed, that means the nucleus is stable. Less energy, the nucleus is not stable. So that's how we make a conclusion about the stability of a nucleus, okay, so based on the binding energy. Okay, so by higher is the binding energy of the nucleus, it is a more stable nucleus. So coming back to the calculation, so the sum of the individual particles of a nucleus, as mentioned, we have to take the total mass of the protons and the total mass of the neutrons. Okay, so therefore the mass defect, okay, so you take the total mass of the protons plus the total mass of the neutrons, you minus the nuclear mass, which is as whole thing. So that will give you the mass defect. So as we discussed. So okay, so here, okay, it may look almost the same, but there's a slight difference. So here the sum of the mass of the individual particles of an atom. Okay, so this one is the individual particles of a nucleus. This is individual particles of a atom. There's a difference. So when you are looking at a nucleus, mean you are zooming to the nucleus. So it is just the mass of the proton plus the mass of the neutron. But when you are looking it as a whole of an atom, then you have the nucleus plus the electrons. So therefore, the total mass has to be the mass of the proton plus the mass of the neutron plus the mass of the electron. You understand the difference? Then, okay, if you want to find the mass defect, so you need to take that mass, you must minus the atomic mass, not the nuclear mass. Because the nuclear mass is only nucleus. When you say atomic mass, then it will take the mass of the nucleus plus the mass of the electron. So when you minus of that, then you will get the difference in the mass, okay, so which is the mass defect. So you must see whether we are based on the atom or based on the proton. I mean, based on the nucleus. So if it's nucleus, then you don't need to minus the electrons. So they will not come in. Okay. So don't memorize this as a formula. See, you can see like, so say this is, don't take it like a formula. You try to understand the logic of looking as the whole atom and looking at the nucleus, zooming into nucleus. Okay. Only when you look at the whole atom, electrons will come into picture. But if you are looking at the nucleus, then electrons will not be in the picture. Okay. So from the binding energy of a nucleus, okay, so when you say binding energy of a nucleus, meaning you are looking at the whole nucleus, all the nucleons inside. So therefore, from there, we can find the binding energy per nucleon. Okay, it's just like when in the chapter thermodynamics, you have specific heat, okay, heat capacity, specific heat capacity. Okay, so the amount of energy required to rise the temperature 1 kg of a substance and the amount of energy required to increase the mkg of a substance. So then you have a specific heat and specific heat capacity. So here also you have seen, you have the binding energy for the whole nucleus and the binding energy for per nucleon. Okay. So this is a binding energy per nucleon. It is the average energy required to remove just one nucleon from the nucleus. Okay, so binding energy per nucleon is the average energy required to remove just one nucleon from the nucleus. So how do you find the binding energy per nucleon? It is the binding energy of a nucleus divided by the total nucleon number. Okay, so the binding energy of the nucleus divided by the nucleon number. This was the graph I was mentioning just now. Please understand this graph. Okay, it will be in a way assessed in your finals. Okay, so binding energy per nucleon here. So if you look at it, this shows how the binding energy per nucleon varies with the mass number. Okay, so mass number is the nucleon number. As you can see, somewhere around, this is actually somewhere around 56. This is somewhere around 56, where the mass number. Okay, 56 is iron. 56 is referring to the iron ferrum. That's why we find ferrum more. Okay, so one of the mineral that is found most on earth is ferrum, because that's one of the most stable. Okay, so if the element is too small, okay, then it will go through. If it is too small, then it will go through a series of fusion reaction, so to become more stable. If the nucleus is too heavy, for example, like uranium is 19204. Okay, so plutonium. So if they are too heavy, then they have to go through a series of fission reactions so that it can break to smaller component. Okay, so it will break to smaller component. So in a way, you can see the process of fusion, the process of fission, it takes to move towards the stable, which is located somewhere around 56. Even recently, I wrote an article, read an article saying that they have found a place where there is a huge amount of iron on Earth. Okay, so this is one proof whereby iron is one of the most stable element. Okay, which has why it is the most stable element? Because you can see from the graph here, it has the highest binding energy. One of the element which has the highest binding energy. So what is the meaning of highest binding energy? So meaning it is the most stable. You need more energy to break the. Okay. So, and you can see in this case, okay, so whether it's too light or too heavy, it will go through a series of this fusion and fission reaction uh, in order to stabilize the nucleus. Okay, so I hope you understand the diagram. No need to know in specific the values, but at least, okay, you know 56 is at a peak, somewhere around peak. Okay, so on both sides, lighter and heavier, okay, you can see the binding energies are lower. So at 56, it has the most, so which is the most stable nucleus. Okay, so this gives you even more precise, okay, detail. You can see. So I don't need to memorize the values. You can see that uranium 238, sorry. So uranium 238, yep. Plumbum, okay, radon. So these are on the higher number of nucleon numbers, which is not stable. If you look at lithium, beryllium, boron, okay, this is on the lighter nucleus, okay, so which is also, okay, so not stable. So maybe the graph is like too light for you to observe here. Okay, so the details is given. So you can see the point here. The region of greatest binding energy per nucleon is shown. Okay. Then here, nuclei to the right of the lead. Okay, so plumbum 208 are unstable because they are too heavy. Too heavy also not stable. Okay, so and the curve represents this one. The curve represents the binding energy for a most stable isotopes. Okay, so that's why this particular curve. So the most stable, okay, so you can see a region somewhere here. Okay. So this is fine. Okay, this is most tightly bond nuclei. Okay, so this is fine. But this shape is important for you to know. Okay, so we will take a break now. You can look into the example 3. Okay, I will put the attendance list. Wait, this was one. Is that? Alright. I know for you too. Take it there first. Yes.
If I need to edit, not edit, to attach these papers of individual submission forms, when can I submit to you the paper?
Okay. You submit that first. So this is one. Okay. So in or later I will be here until 10:30 until 1 o'clock. I will be until 12:30. I will be in the staff room. You can discuss over.
And after that, then,
Wait, wait.
yeah, I'm not sure I will have time to gather all the members to put them to sign.
Because I will be here because in between I have tutorial sessions.
On Friday. Friday we have lecture.
Yeah, no, this week Friday. Okay, so I did mention, so I will be on leave.
Right, but
Wait,
right now I can submit what I have, right?
Yes, I think better. I mean that. Yes. Okay, you can take it to the table. Okay, so you can take everything to take. Okay, thank you. Here, on top,
Right.
here, write your class group. Okay.
By some class. We happen to do the same topic. I mean, the YouTube video, which is the same YouTube video. Yeah, we play the video on. Yes. They're like two guys, like American. Syrian.
Okay, I think there was another group also did, and they demonstrated, they did an experiment on that.
So we have the same topic.
Okay, so that's fine. But then your report, that's okay.
Just to make sure if you see two same topics.
Okay. Yeah, so I will look into your report details. Okay.
How about the quiz?
Huh?
The master.
Okay, so quiz. Okay, so I will arrange a time next week. I will want to see each group, then I will give one, because one shot is difficult to handle. So I will advise that on that. Okay, so probably I will give a time frame. Okay, so then the group come in. Okay, so I will give the papers. Okay, so you can take your picture. Then you will return the paper. Not this Friday I will be on leave.
Yeah. So it will be online or
No class. No class.
Sorry,
No. Okay, so I will, because the now ruling, you cannot, any replacement class cannot be done online. So if it is a physical, you have to do physical. So then because when I submitted, they said, okay, cannot, you need to change. So I have pre-submitted. So the classes will be done. I will update on that in the Teams. Okay. So Friday, no class. That one I will tell, of course.
Like group assigned like four picture so like but so our first number like we couldn't find like people could just
Leaving.
okay.
So okay, then you sign on top. Which two? Come, students. Okay, a few things. Just tell you, I will update in Teams because when I carry it out, okay, so always I can see this confusion takes place. Okay, so but okay, just to inform you, this week Friday, okay, so physics no lecture. Okay, so tutorial no, because I will be on leave. Okay, so for the groups, I mean lecture. Okay, yes, there's no. for the groups which is having tutorial, also no. And then initial, okay, so the group supposed to have the tutorial with me on Friday is the group 6, physical science 6, and also physical science. The tutorial, okay, so we cannot have it. This is the from the May 13 onwards. Okay, the ruling, okay, so of the higher education, okay, so Siaman, no replacement class. If it is a physical class, no replacement of the class, okay, so online, okay. But if it is the public holiday, okay, so that is different. So, but if for leave, any annual leave taken, okay, so leave replacement, okay, so it has to be replaced also physical. Therefore, okay, so the tutorial class scheduled initial plan to have it Friday evening, so no, okay, but then we will have that classes, okay, so next week Friday physical, meaning you will have normal one, okay, and then the later. So I will update that. So I don't want to further explain, then everyone will get confused. So just this week Friday, no, okay. And the lecture for the what's that Friday lecture, so which is supposed to be the lecture 18. So that will be replaced on Thursday evening. Okay, next week Thursday, which is on the 12th. Okay, so evening. So that day actually I don't come to office, but then I have no choice. Okay, so I need to put it on Thursday evening, 5:15. So I have to just come for the class. Okay, so the evening. So that will be physical. Okay, so because I could not slot in this week because again another problem is the venue. This venue is been booked. Okay, so for evenings. So even next week also, Monday, Tuesday, Wednesday, the venue is booked. So I can only book on the Thursday and Friday. So that's why I choose Thursday because Friday you're already having a lecture. So I don't want to have a double. Okay, so at least I can do it on the Thursday. Okay, anyway, I will update that in your teams. Okay, so take note this week Friday. Okay, so lecture from me, physics for TMP. If you have any other for your other classes, I mean other teachers, yes. Okay, let's move on. Example 3. Did you try? The atomic mass of a carbon 12 atom is 12.0 U. So this is the atomic mass. So you need to be very careful with the information given. So here you understand this is referring to the atomic mass. Okay. Determine the binding energy of carbon 12 and the nuclear binding energy per nucleon. Okay. So how do you work that? So binding energy for carbon 12. So what is given is the atomic mass 12.0 U. So this one you need to find the mass. Okay, so if it is 12, then 12.0, okay, I don't put the 0. Okay, times the unified atomic mass value. Okay, so that is 1.66 times 10 power of minus 27. So this will give you in kg. So that is the atomic mass. Okay, so now you need to find the mass for the proton and neutron and electron because what is given is the atomic mass. So if you follow the equation just now, okay, so for the so I have 6 proton, mass of proton, plus 12 minus 6, that will be the mass of the neutron, plus, okay, so that is the total what do you put for electron? How many electrons are there? How many electrons are there? 6 also, because proton you have 6, mean electron has to be 6 because this is a neutral. So 6 mass of the electron. Okay. So this will find the total mass of the proton, neutron, electron separately. Okay. So that will give you separately. So once you have found that, what do you have to do? Okay, so you have to follow the 6 times. Okay, you don't need to substitute the values. You can just use the value MP, MN, and ME. Okay, so what you can do is, okay, so times by 6, times by 6, times by 6. So then you add them up. Okay, so that will give you the total mass for the proton plus neutron plus the electron. Okay. So you please work it out lah, because this one will, when you multiply huge numbers, okay, everyone will have a different speed of calculating. So I can't be like waiting. Okay, so work out this. Okay, when you get these values, okay, so that's where it comes into this formula here. Okay, so you add them, you should get your answer, okay, as what I have. Okay, I'll write the answer. So when you work it out, so it should be 12.09894 U. Okay, you will get that. Okay, so that is the mass of the proton, neutron, electron when you add up separately. But then when they form the atom, the atomic mass is only 12.0 U. So now if you want to find the mass defect, it will be 12.09894 U, U minus 12 U. Because that is the atomic mass when they come together. Okay. So the difference is equivalent to, when you minus, okay, so 0.09, oops, 9894 U. Okay. So that is the mass defect. So once you know the mass defect, the next step is you can go to the formula E equals to delta MC squared. Okay, so but then obviously you need to change that to the U, you need to change to kg lah. So if 0.09894 U, okay, so you change to kg, you multiply by 1.66 times 10 power minus 19. Sorry, minus 27, sorry. 1.66 times 10 power of minus 27. That will give you the mass defect in kg then you multiply by the speed of light square. Okay, or just now there was an assumption that 1u is equivalent to 931 something. You follow the question. If the question have given you the assumption equivalent, where is it? This value 931.5. 1u is equivalent to 931.5 MeV. So you can also use that to solve this. So you can straight go to, okay. So you can just take as 0.09894 u, how much? So you just take 0.09894, you multiply by 931. Okay, so 0.09894. Okay, so you multiply by 931.5 MeV. Sorry, should have given us some space here. So I can take this as 0.09894 times 931.5 MeV. Okay. Provided this one, the constant is given in the exam. Okay, so if this value was given, you follow accordingly. So 1u equivalent to how much? So then accordingly, okay, you can just multiply. Otherwise, okay, so otherwise, or you need to traditionally calculate out lah. So 0.09894 multiplied by 1.66 times 10 power of minus 27. Then you multiply by your speed of light square. Okay. And then in this case, you will get your answers in joule. Okay, in joule, then you can convert to MeV if the question want your answers to be given in MeV. Okay, so you just follow according to the question. So the question does not mention whether they want the answers to be in joules or MeV. So fine. Then B, once you get your A, B is, how do you get your B? The nuclear binding energy per nucleon. Okay, what was the answer here? So when you find 0.09894 times 931.5 MeV, what do you get? 92.60, yeah. 16. Oh, okay. So 162, I think 1620 MeV, correct? Okay. So that is the binding energy of the nucleus. Okay, so if you want to find the binding energy per nucleon, so then you will take 92. So you will take 92.1620. You divide by what? Yeah, 12. Because 12 is the nucleon number. So you must base on the nucleon number divide by 12. So that gives you the binding energy per nucleon. Okay, so which should be somewhere about 768 MeV, I think. Do you get it? Okay. So this is a binding energy for nucleons. Okay, so where that particular for nucleus, where that nucleus has nucleons. Okay, now I ask you a question. The other questions, okay, so example 4, example 5, 6, Okay, you can see the graph comes in. So some of the answers are there. Okay, so the one does not have the answer. Okay, 3, 4. Okay. I'll give you the answer for 4. So given that the mass of the helium nucleus, okay, so find the binding energy of the helium. Okay, so binding energy of the helium. So you should get your answer as 28.36359 MeV. Okay. Question number 5. Find the mass defect. So the mass defect delta M is equivalent to 0.118 U. Question number 6. A is the binding energy. So it is 1270 MeV. B, the mass defect is 1.36 U. Okay. Extra question 7. Find the mass defect. Okay. So this again, the answer's mass defect. Okay, given. Question number 8. The energy. Okay, so yes, given. Extra question 9. Okay, so calculate the binding energy. Calculate the binding energy. Binding energy is not given. So the binding energy, okay, so should be 79.0. So this one, the answer is given. Okay, so 0.0848 U. Okay, so question number 10. I think this is correct. Sometimes it depends on which approach. So this one, okay, so if you use the assumption of 1U is equivalent to 931.5 MeV, then you will get this answer. But if you are going to use the formula E equals to delta mc squared, you want to put it in kg, then probably you will end up getting an answer slightly different, 225.49782 MeV. So in the exam, no worries. Okay, so if you use this method, then you are expecting slightly different. So it will be accepted in both ways because it involves a large number of decimal places. So definitely when you use different calculation, the assumptions may lead to a rounding up of the values. Okay. 11. Binding energy, okay, so 1 to 7 and 7 and okay, fine. So always you may find slightly different takes place, it's okay. Okay, if there is a slight difference, fine. Okay, so then question number 12. Okay, so that goes into the radioactive decay. That one, okay, so once I see you next week, Wednesday. Okay, so then in the next week, Wednesday, I will continue from this part. Okay, just hold on. So basically, okay, next week, okay, so we will be looking into the further discussion about the radioactive decay and decay constant half-life. Oh, hey, you come in late, you want to go back fast. Okay, wait. Okay. So if you find some time, okay, so over the weekend, it's quite interesting for the radioactivity part. Okay, so you can just go through on this. This graph I did mention earlier. Okay, so but then it is more of discussion about alpha, beta, gamma, decay process, some things that you have learned in your IGCSE or SPM. Okay, so just see. Okay, so go through. My main thing, try to finish the example patients. Okay, so up to 11. Okay, so thank you, students. Yeah. For presentation. 1U. Eh? This is 1U. The value of 1U. You go earlier slide, you will find out. Anything equivalent to 1U have a mass of this. C is the speed of a light. That's the speed of a light. Okay, 3 times 10 power of 8. Yes, yes. Which box? Okay, okay, I will put a box outside. Okay, Varana. Yes, moment. Yeah.
This it always like we get actually we get stress
Yes.
stress is the
Mass of 1U.
not change right.
This one is in kg. It's a constant. It will not change. Yeah. Next week I will give, because I will give a time slot. Okay, so each group to come in, I will give your paper. You can see, you can take picture. Next week. Not this week, not this week. But initially I plan this week, but then tomorrow and Friday I won't be around. And I just don't want to, because I thought I can pass to those who, because not everyone I'm seeing for tutorial. So if I do for my group, which is I doing tutorial, then not fair for the other students. So I must make sure everyone able to see. Yeah.
A consultation for thermodynamics and have questions like, for example, from presentation examples and from tutorials.
Mhm.
I give a book consultation with you because Dr. Chen teaches us tutorials, not
Come here.
like if a book
Consultation. Consultation, you have to come to me. Tutorial questions, okay, it's okay. No problem. Because I'm a first so you can ask him.
Okay.
You can if Dr. Shine is available, you can ask him. So otherwise, you can ask him.
I think before finals in week 11 and 12, still okay, right?
Yes. So tentatively, okay. So I will try to put in a time slot where you all can meet me. So then in between, okay. So I will be probably I will be in the staff room. If you call, then I can come out and explain to you. Okay. Yes. Okay. Wait.
Oh, this part after because my degree maybe I decide to go to UM.
Boy. This one,